Added the marker. All right, well, we'll add this marker now. And let's go ahead and turn off. I'm gonna hide the game so it doesn't, bother anybody. If you can still play it behind the scenes, so it's still like running. It's just not visible. And we are going to start with bytecode. Okay, so intent. Give behavior the flexibility of data by encoding it as instructions for a virtual machine. Motivation. Making games may be fun, but it certainly ain't easy. Modern games require enormous, complex code bases. Console manufacturers and app marketplace gatekeepers have stringent quality requirements, and a single crash bug can prevent your game from shipping. Maybe that's true now, but I don't know, like would Steam stop you these days? I worked on a game that had 6 million lines of C++ code. For comparison, the software controlling the Mars Curiosity rover is less than half that. At the same time, we're expected to squeeze every drop of performance out of the platform. Games push hardware like nothing else, and we have to optimize relentlessly just to keep pace with the competition. To handle these high stability and performance requirements, we reach for heavyweight languages like C++ that have both low-level expressiveness to make the most of the hardware and rich type systems to prevent or at least corral bugs. We pride ourselves on our skill at this, but it has its cost. Being a proficient programmer takes years of dedicated training, after which you must contend with the sheer scale of your codebase. Build times for large games can vary somewhere between go get a coffee and go roast your own beans, hand grind them, pull an espresso, foam some milk, and practice your latte art in a froth. On top of these challenges, games have one more nasty constraint: fun. Players demand a play experience that's both novel and yet carefully balanced. That requires constant iteration, but if every tweak requires bugging an engineer to muck around in piles of low-level code and then waiting for a glacial recompile, you've killed your creative flow. Spell fight. Let's say we're working on a magic-based fighting game. A pair of wizards square off and fling enchantments at each other until a victor is pronounced. We could define these spells in code, but that means an engineer has to be involved every time one is modified. When a designer wants to tweak a few numbers and get a feel for them, they have to recompile the entire game, reboot it, and get back into a fight. Like most games these days, we also need to be able to update the game after it ships, both to fix bugs and to add new content. If all of these spells are hard-coded, then updating them means patching the actual game executable. Let's take things a bit further and say that we also want to support modding. We want users to be able to create their own spells. If those are in code, that means every modder needs a full compiler toolchain to build the game, and we have to release the sources. Worse, if they have a bug in their spell, it could crash the game on some other player's machine. Data is greater than code. It's pretty clear that our engine's implementation language isn't the right fit. We need spells to be safely sandboxed from the core game. We want them to be easy to modify, easy to reload, and physically separate from the rest of the executable. I don't know about you, but to me that sounds a lot like data. If we could define our behavior in separate data files that the game engine loads and executes in some way, we can achieve all of our goals. We just need to figure out what execute means for data. How do you make some bytes in a file express behavior? There are a few ways to do this. I think it will help you get a picture of this pattern's strengths and weaknesses if we compare it to another one, the interpreter pattern. The interpreter pattern. I could write a whole chapter in this pattern, but 4 other guys already covered that for me. Instead, I'll cram the briefest of introductions in here. It starts with a language, think programming language, that you want to execute. Say, for example, it supports arithmetic expressions like this. So you have 1 plus 2, you have parentheses around it to make sure this happens first, 3 minus 4, and then you take whatever these two are, so 3 and 1, 3 and -1, and multiply them against each other. Then you take each piece of that expression, each rule in the language's grammar, and turn it into an object. The number literals will be objects. Okay, so 1, 2, 3, and 4. Basically, they're little wrappers around the raw value. The operators will be objects too, and they'll have references to their operands. If you take into account the parentheses and precedents, that expression magically turns into a little tree of objects, like so. Okay, so multiplication happens first. Oh, so the first things are at the top of the tree so that they happen last, because you have to delve into the tree and then reverse back as you do it. That's clever. Yeah, okay, so it's taking like the 1, 2, 3, and 4 come from here. And then we're saying, okay, multiplication happens, and then these two are added together. So it's the like we're creating a tree. I guess there's no thing that this has to be binary tree, although it's accidentally become a binary tree. What magic is this? It's simple. Parsing. A parser takes a string of characters and turns it into an abstract syntax tree, a collection of objects representing the grammatical structure of the text. Whip up one of these and you've got yourself half of a compiler. The interpreter pattern isn't about creating that tree, it's about executing it. The way it works is pretty clever. Each object in the tree is an expression or a sub-expression. In true object-oriented fashion, we'll let expressions evaluate themselves. First, we define a base interface that all expressions implement. Okay, so here's where the fun code starts. So let's create a new folder. Actually, not here. In playgrounds, create a new folder called Bytecode. And in reality, I guess this is it's more of like the chapter, so we can find where it is. But this is the interpreter pattern. So I'm going to call this interpreter.js. Okay, so we'll start by changing this over into JavaScript. So we have a class expression. We don't use the one true bracket pattern. We have this this method expression. Now it's virtual here, which means it doesn't truly exist. So it can just be like this. And then we have this evaluate. So that would be in a constructor. And in the constructor, we can take evaluate and make it this dot evaluate equals to 0. Nope, I didn't need to destroy the expression. Okay, so that's basically what we have here. Is we have an empty expression that's meant to be used by whoever inherits or extends expression. And I'm thinking I'll probably go to the end of this section and then redo this in Rust. So then we define a class that implements this interface for each kind of expression in our language's grammar. The simplest one is numbers. So numbers is an expression. Let's see what they mean. So number expression. We want extends expression. Okay, so we have number expression, which takes in a value, and it just sets that to be internal. So I'm going to create a constructor. This dot value equals. I mean, we might be able to say this is sort of like null. Oh no. I keep on forgetting. When it's the exact same name in C++, that's the constructor. So when we start this, we create a value, and we're saving that in here. That's what's happening here. Then we have this evaluate, which is not from this expression. We just have this evaluate, which returns this dot value, and then we have the value. Okay. A literal number expression simply evaluates to its value. Addition and multiplication are a bit more complex because they contain sub-expressions. Before they can evaluate themselves, they need to recursively evaluate their sub-expressions, like so. So then we would have an addition expression. Which extends expression. So we're probably gonna have a constructor here. So addition expression, we're gonna take an expression, which is gonna be on the left. So whatever is on the left and whatever is on the right. And then we're gonna store those internally. So this dot left equals left. This dot right equals right. Virtual double, so evaluate now. So finally we're going to implement, no, same thing. I keep on thinking we're gonna implement expression, but I guess, oh, you know what? It's because expression is the, never mind. That's the constructor. Okay, so evaluate. I'm surprised. Was evaluate not a virtual double? Oh, okay. So they did have evaluate, which is a function. So I think that's the key here. Is this is not. This is evaluate, which is like this. Which I suppose by default just returns 0. And then we need to call super on all these. Super, and there's no constructor to add in. So that gives us that evaluate. Okay, so back to addition expression. So we've stored the left and right. And then we want to return left plus right. Oh, so an evaluate. What we want to do here is, so const left equals this dot left dot evaluate. Const right equals this dot right dot evaluate. So those just become the numbers that they get out. So that's why we did that evaluate on pure numbers. And then we can return left plus right. Okay, that works. I'm sure you can figure out what the implementation of multiply looks like, which would be very similar to that. It's just multiply. Pretty neat, right? Just a couple of simple classes, and we can now represent and evaluate arbitrarily complex arithmetic expressions. We just need to create the right objects and wire them up correctly. Ruby was implemented like this for something like 15 years. At version 1.9, they switched to bytecode, like this chapter describes. Look how much time I'm saving you. It's a beautiful, simple pattern, but it has some problems. Look up at the illustration. What do you see? Lots of little boxes and lots of arrows between them. Code is represented as a sprawling fractal tree of tiny objects. That has some unpleasant consequences. Loading it from disk requires instantiating and wiring up tons of these small objects. Those objects and the pointers between them use a lot of memory. On a 32-bit machine, that little arithmetic expression there takes up at least 68 bytes, not including padding. If you're playing along at home, don't forget to take into account the vtable pointers. Traversing the pointers into sub-expression is murder on your data cache. Meanwhile, all those virtual machine method calls wreak carnage in your instruction table. See the chapter on data locality for more on what the cache is and how it affects your performance. Put those together, and what do they spell? Slow. There's a reason most programming languages in wide use aren't based on the interpreter pattern. It's just too slow, and it uses up too much memory. Let's go ahead and now do this in Rust. So open up View. We're now in interpreter. Cool. I misspelled the other one. Okay, so if I copy in like what we have here. So obviously you're super upset at me. Let's maybe not do that. Let's just come back up here and start over again. So we start with this class expression, but this expression is not being used itself at all. It's being used only to set up like these virtual sort of fields for it and for extensions. But there's no inheritance in Rust. So this is as close as we could come to like a trait expression. And then we notice that there's there's two methods here. Oh, there's the constructor, which we don't have to worry about that. And then there's evaluate. So we're gonna have a function evaluate. That's gonna take in self. It's not gonna do anything to itself. And it's going to return, and it looks here like it's being set to return like an int. Now that being said, if we want like floats or other type of other types of like strings or something else, this would have to be some kind of generic that we do. For right now, if we just stay to the ints, because we know that they're ints, then let's do I32. Because we know they're full numbers. At least they seem to be. Okay, so that's our trait. And now we can create our actual expressions that are based upon this trait. So we're going to have a struct number expression. And inside of here, we're going to store the value, which according to this is going to be our I32. Or if we need to make like whatever our expressions are generic, then we can do that here too. Then we're going to have our evaluate on this. So they want a constructor. We don't actually need a constructor with this. We could just store the value when we create it. We can now impl expression for number expression and function evaluate. We take in self. We know we have to return an I32. And so for this number expression, we're just going to return. We don't even have to have the return. It's just going to be self. I think I just do self. What is it going to be? Self dot value. I was going back and forth between like, do I need colon? Do I need dot? Do I need right arrow? That's too many alternate languages that I've been going back and forth with. And so that gives us that. So now we can use like create a number and then create that value. Okay, so let's do addition expression. So we're gonna have struct addition expression. And so in here, we know we're gonna need like a left and a right. So we have a left And we know that this is going to be an I32 simply because all of our stuff here are I32s. Otherwise, again, they'd have to be generics. So write I32. And then, so here when we create the new one, this one might be easier to put in some kind of a constructor essentially with it, which would be where we hand in the left and the right. Because it's going to take the expression left and expression right. So yeah, let's do, so impl addition expression, we're going to have a pub function new. And in here, we're going to take in left, which is a number expression, and right, which is a number expression. We're going to return let's go ahead and make this full screen. We're going to return an addition expression. Okay, so this is going to be addition expression. Left is going to be left dot evaluate. Right is going to be right dot evaluate. And so then we can now implement evaluate. Oh no, we're just storing, okay, never mind. I forgot, we're just storing not the actual numbers here. These are going to be number expressions. So we're just straight up taking ownership of these and storing them in. If we need to store the references to them, that's a completely different thing. And potentially a different structure would be better for that, so we don't have to deal with lifetimes. But okay, now we want to impl expression for additional expression. Function evaluate, which takes in self and returns an I32. And so here we're going to say, first we need to get like the actual left and right. So let left equals self dot left dot evaluate. Let right equals self dot right dot evaluate. And they're going to return left plus right. And that's the code for that. If any of you have any questions, please feel free to ask. Let me, because I forgot to add it on, I'll turn on the Twitch highlighter too, so that you can highlight any lines that you want me to explain, or if I make any mistakes. Machine code virtually. Consider our game. When we run it, the player's computer doesn't traverse a bunch of C++ grammar tree structures at runtime. Instead, we compile it ahead of time to machine code, and the CPU runs that. What's machine code got going for it? It's dense, it's a solid contiguous block of binary data, and no bit goes to waste. It's linear, instructions are packed together and executed one right after another, no jumping around in memory unless you're doing actual control flow, of course. It's low level. Each instruction does one relatively minimal thing, and interesting behavior comes from composing them. And it's fast. As a consequence of all these, well, and the fact that it's implemented directly in hardware, machine code runs like the wind. This sounds swell, but we don't want actual machine code for our spells. Letting users provide machine code which our game executes is just begging for security problems. What we need is a compromise between the performance of machine code and the safety of the interpreter pattern. What if instead of loading actual machine code and executing it directly, we defined our own virtual machine code? Then we'd write a little emulator for it in our game. It would be similar to machine code, dense, linear, relatively low level, but it would also be handled entirely by our game so we could safely sandbox it. To be fair, that's the only chapter of the book I think is kind of far-fetched. I would 100% go to a known embeddable language instead of implementing my own, like Lua or some Rust-like equivalent. But for sure, the pattern is useful. Yeah, this is starting to look like implementing a full language, which might be fun. But yeah, this might be a little bit overkill, especially for. I could see maybe he's talking about this for like AAA games, or maybe it's actually useful for that. This is why many game consoles and iOS don't allow programs to execute machine code loaded or generated at runtime. That's a drag because the fastest programming language implementations do exactly that. They contain a just-in-time compiler, or JIT, that translates the language to optimized machine code on the fly. We'd call our little emulator a virtual machine, or VM for short, and the synthetic binary machine code it runs, bytecode. It's got the flexibility and ease of use of defining things like in data, but it has better performance than higher level representations like the interpreter pattern. In programming language circles, virtual machine and interpreter are synonymous. I use them interchangeably here. When I refer to the Gang of Four's interpreter pattern, I'll use pattern to make it clear. This sounds daunting, though. My goal for the rest of the chapter is to show you that if you keep your feature list pared down, it's actually pretty approachable. Even if you end up not using this pattern yourself, you'll at least have a better understanding of Lua and many other languages which are implemented using it. I have always wondered how to sort of like add in a modding system into a game, and it sort of sounds like this is like at least part of that. The pattern. An instruction set defines the low-level operations that can be performed. A series of instructions is encoded as a sequence of bytes. A virtual machine executes these instructions one at a time using a stack for intermediate values. By combining instructions, complex high-level behavior can be defined. When to use it. This is the most complex pattern in this book, and it's not something to throw into your game lightly. Use it when you have a lot of behavior you need to define and your game's implementation language isn't a good fit because it's too low level, making it tedious or error prone to program in. Iterating on it takes too long due to slow compile times or other tooling issues. It has too much trust. If you want to ensure the behavior being defined can't break the game, you need to sandbox it from the rest of the code base. Of course, that list describes a bunch of your game. A bunch of your game? Who doesn't want a faster iteration loop or more safety? However, that doesn't come for free. Bytecode is slower than native code, so it isn't a good fit for performance-critical parts of your engine. Keep in mind, there's something seductive about creating your own language or a system within a system. I'll be doing a minimal example here, but in the real world, these things tend to grow like vines. For me, game development is seductive in the same way. In both cases, I'm striving to create a virtual space for others to play and be creative in. Every time I see someone define a little language or a scripting system, they say, "Don't worry, it'll be tiny." Then inevitably they add more and more little features until it's a full-fledged language. Except, unlike some other languages, it grew in an ad hoc, organic fashion and has all the architectural elegance of a shantytown. For example, see every templating language ever. Other languages that are like really, really popular that have sort of like done that. I know that PHP grew in this sort of way. Perl, I think, grew in this way, and then they had to do these like major refactors later to sort of switch over. Of course, there's nothing wrong with making a full-fledged language. Just make sure you do so deliberately. Otherwise, be very careful to control the scope of what your bytecode can express. Put a short leash on it before it runs away from you. So yeah, it sounds like to me, it's like, okay, I could create my own language. Or we could just use Lua for that, which would be perfect. Making a mod engine is very interesting because you usually end up having a C-compatible API, so likely to evolve into a use whatever language for your mod. This is also like sort of what I was a long time ago. I don't know if any of you were around physics. I wonder, were you around? You might have been. When like a couple years ago, I started making a game for like a bot arena game where bots are going to fight against each other, and I had to figure out how to run other people's code. And you making them just, I wanted them to be able to use whatever language they wanted to, but at the same time, I could have just said, you know what, you're using Lua, and then we're gonna sort of implement it as a plugin, like a modding almost level. And I wonder if this is going to be a very similar thing. You'll need a front end. Low-level bytecode instructions are great for performance, but a binary bytecode format is not what your users are going to author. One reason we're moving behavior out of code is so that we can express it at a higher level. If C++ is too low level, making your users effectively write in assembly language, even one of your own design, isn't an improvement. Unless that's the point. Challenging that assertion is the venerable game RoboWar. In that game, players write little programs to control a robot in a language very similar to assembly, and the kind of instruction sets we'll be discussing here. It was my first introduction to assembly-like languages. Is RoboWar still around? It's to the Wikipedia. It's not even to the website for that. I vaguely remember RoboWar, and I also remember that I don't think it exists anymore. Much like the Game 4's interpreter pattern, it's assumed that you also have some way to generate the bytecode. Usually, users author their behavior in some higher level format, and a tool translates that to the bytecode, and our virtual machine understands. In other words, a compiler. I know, that sounds scary. That's why I'm mentioning it here. If you don't have the resources to build an authoring tool, then bytecode isn't for you. But as we'll see later, it may not be as bad as you think. WASM for the use whatever language you want. That's true, because WASM is a compiler target, and it's going to be the same for everyone. So that kind of makes sense. That being said, WASM with the target being not a browser would be very fascinating. I wonder if anybody's going to actually do that. You'll miss your debugger. Programming is hard. We know that we know what we want the machine to do, but we don't always communicate that correctly. We write bugs. To help find and fix those, we've amassed a pile of tools to understand what our code is doing wrong and how to do it right. We have debuggers, static analyzers, decompilers, etc. All of those tools are designed to work with some existing language, either machine code or something higher level. When you define your own bytecode virtual machine, you leave those tools behind. Sure, you could step through the VM in your debugger, but that tells you what the VM itself is doing, and not what the bytecode is interpreting is up to. It certainly doesn't help you map that bytecode back to the high-level form it was compiled from. If the behavior you're defining is simple, you can scrape by without too much tooling to help you debug it. But as the scale of your content grows, plan to invest real time into features that help users see what their bytecode is doing. Those features might not ship in your game, but they'll be critical to ensure that you actually can ship your game. Of course, if you want your game to be moddable, then you will ship those features, and they'll be even more important. Look it up when you got time. WASM sounds very interesting. I haven't looked at WASM in a long time. I would be fascinated to see how far it's come. I've seen more and more articles coming out on it, so. It's an aberration to you because there's web in the name. But it allows you not to write JavaScript as much. So there is that. Sample code. After the previous couple of sections, you might be surprised how straightforward the implementation is. First, we need to craft an instruction set for our VM. Before we start thinking about bytecode and stuff, let's just think about it like an API. A magical API. If we were defining spells in straight C++ code, what kind of API would we need for that code to call into? What are the basic operations in the game engine that spells are defined in terms of? Most spells ultimately change one of the stats of a wizard, so we'll start with a couple for that. So this is an API, but is this in a class? maybe. Oh, int wizard, like the location of a wizard in an array, maybe. The first parameter identifies which wizard affected, say 0 for the players and 1 for their opponent. This way, healing spells can affect the player's own wizard, while damaging attacks harm their nemesis. These 3 little methods cover a surprisingly wide variety of magical effects. If the spells just silently tweak stats, the game logic would be fine, but playing it would bore players to tears. Let's fix that. So then we have spawn particles. This sounds like it might be in like the game loop. So if we come back to here, yeah. So in bytecode, now we're in bytecode. So bytecode.js. So here we have our set withers. I don't know where this is like in the code base, so we're just gonna create it into here. And so it looks like this is a function on some kind of class. I guess it might be like wizards that it's doing, but I don't know off the top of my head. So let's go ahead and just, because if I have a class wizards, and we have a constructor, so this dot, essentially it's going to be wizards is an array. And so if we're going to put those into there, then we can now have these methods. So like set health, which is going to take a wizard, and it's also going to take an amount. And so I guess he's setting these as like an interface, isn't he? So I guess this is something like this, where we're creating the abstract methods for it. So it's like set health, then we have set wisdom, which takes the, I should create these as like wizard ID. Let's make it a little bit more obvious what's happening. So amount, then set agility, which is wizard ID and amount. Okay, and so then in like, I guess the game loop, we're gonna have play sounds and spawn particles. We just don't know where that happens compared to this. Like when we set the health, I guess we also like inside of here, this is where we play the sound. It sounds like it might be part of like a world or something. So we have play sound, sound ID, and spawn particles. So this could be like a particle ID, particle type. This is like, I'm not completely sure that this is wizard, or if it's going to be something like world. It might make more sense to be world, and then the game loop is basically going through and running these. Now, if I wanted to do this exact same thing in Rust, because we're at the sort of end of this subsection, let's go ahead and create a new file here. We'll call this bytecode.rs. So this is going to be a little bit more interesting. We're not even going to have to set these up, because these are just, I mean, essentially interfaces, the interface for it. So this is going to be a trait. And a trait on a wizard I'm gonna think is a trait on a wizard. This might be a trait like on a world. Or like on the game. Something like that. Or it might be like magic. So here we have function set health, which takes a wizard ID, which is an I. They're almost always like U size. And then an amount, which let's just say is a I32. Function set wisdom. So that takes a wizard ID, which is a U size. These also will probably have to take a mutable reference to self. Okay, so we have the wizard ID, and then we have the amount, which in this case, again, an I32. And then set agility. So function set agility self. So we have the wizard ID, which is a U size. And we have the amount, which is an I32. And then we have these like place sound and spawn particles. And the question is like, are they really part of this? Probably they are, because whenever you're doing this, you also need to run these. And so like until I know like where they go, I'm just gonna have this be on magic. So we have a we have a struct that's gonna be, implementing all of these. So now we have place sound, which takes in reference to self, and sound ID, which is a U size, and function spawn particles, which takes in, this probably is like mute self or some, anything that with spawn it, that sounds like mutable. We're gonna add them into our world, as it were. And we have now particle type. Now, so this is interesting because they have an int for a particle type, but it makes a lot more sense to me that we'd have an enum particle type. And so this could be something like, I don't know, blue magic or something like that. I wonder if I can. And so now your type is going to be particle type. And so that way we don't need to like go look it up. We just have exactly what it is. If we need to have some kind of ID and something else, we can store that inside of the enum. All right. These don't affect gameplay, but they crank up the intensity of the gameplay experience. We could add more for camera shake animation, but this is enough to get us started. A magical instruction set. Now let's see how we turn this programmatic API into something that can be controlled from data. Let's start small, and then we'll work our way up to the whole shebang. For now, we'll ditch all the parameters to these methods. Oh, okay. We'll say the set methods always affect the player's own wizard and always max out the stat. Likewise, the FX operations always play a single hard-coded sound and particle effect. Given that, a spell is just a series of instructions. Each one identifies which operation you want to perform. We can enumerate them. Okay, so instruction, and then we have set health. Interesting. What are these? To encode a spell in data, we store an array of enum values. We've only got a few different primitives, so the range of enum values easily fits into a byte. That means the code for a spell is just a list of bytes, ergo byte code. Is this the locate? This can't be location of memory. Can it? I'm not used to like C++, so I don't know what this is. Some bytecode VMs use more than a single byte for each instruction. Oh, that is, isn't it? This is like a byte in memory. And have more complicated rules for how they're decoded. Actual machine code on common chips like x86 is a good bit more complex. But a single byte is good enough for the Java virtual machine and Microsoft's common language runtime, which forms the backbone of the .NET platform, and therefore it's good enough for us. To execute a single instruction, we see which primitive it is and dispatch to the right API method. So we're going to have our switch statement, so switch instruction, which we're coming in from this. Case sit, so like if it's which one of these it is. And then we call, set health. Interesting. And then that's the wizard ID, and then the value. So we're just gonna set you to full health, and we do all of these. In this way, our interpreter forms the bridge between code world and data world. We can wrap this in a little VM that executes an entire spell, like so. Okay, so finally we're getting into real code here. So class VM, we have interpret. So we take in the array of bytecode, and then a size. We're going to loop through using the size here. Instruction equals bytecode of I. Do we have the instructions yet? I don't think we do. And then call switch in, and then have our switch statement for the instructions. Type that in and you'll have written your first virtual machine. Unfortunately, it's not very flexible. We can't define a spell that touches a player's opponent or lowers a stat. We can only play one sound. To get something that starts to have the expressive feel of an actual language, we need to get parameters in here. So let's start with this. So back to the JavaScript side. So it sounds like this is, I don't even know if we need this part. We're certainly gonna have to rewrite that. Basically, we're gonna have our instructions. So const instruction in enum. I'm gonna call it an enum because there's no way to really truly make enums in JavaScript. Instead, we have to do basically what this is in here. So we have like, essentially it's like set health, which is, set health. Let's just do set like that. And if I do like one more, set wisdom. Okay, so that gives us our instruction set. Now, if we come down to here, we're going to get our VM. So we have a class VM. Now, it doesn't look like we have a constructor on this. Instead, we just have the interpret method. So interpret, which takes in bytecode. And it takes in a size. We need to loop through the bytecode. Interesting, so we're taking the size and we're taking the bytecode. Is that also like the size? Because I kind of wonder, like, why can't I just for each the the bytecode itself if it's just an array. Because instruction of bytecode, yeah, we're getting like the length of the bytecode, so we kind of don't even need this. We could just do this with a for each here. So this is going to be bytecode. So just to make sure that this knows what it is, I'm going to set the default to an empty array here. So then for each, we essentially have the bytecode, and so now we're going to call. We're going to get the instruction, and we're going to run. Then we're going to have the switch for this instruction. So in here, now we have our switch. So switch on bytecode. Oh man, it's been forever since I created a switch for this. So if bytecode is equal to, can I do case? Case, and it's going to be essentially, we're getting handed like one of these. This should probably, now that I think about it, this should probably be equal to that. Mainly because I'll be able to say if case of instruction enum of position BC. So if that's truthy, then we can run whatever this is. You have to do like colon. Yeah. And then it's going to be like set health 0. So now we're going to run these. So if I now have these not part of view, essentially we now have all these as functions. Like that. So in this case, we're now gonna call set health, pass it like 0 is the ID, and then the amount is full up to 100, and then break. Because if you forget to break in a case, it's terrible. This is one of the reasons I don't use cases very much, because I know I'm gonna forget. And of course we have the other one, so let's do set wisdom next. So we're gonna have case, set wisdom. Oh, instructional. Wait, can I? How do I set, like, figure out which one of this is? Is this like a statement? Oh man, I forgot how to do switch statements. Is it like case? Oh, it's gonna be, okay, so switch, hold on. You're gonna be instructional enum of BC. And then that's where we're gonna do case this. Set like health. And then we're gonna have case, okay, set wisdom. And I guess like I could also do, if I want to like potentially change these around, this could be instructional enum dot set wisdom. Like that. And so then this is set wisdom of 0 and 100. Okay, that's what we want to do. So instead of set health, it's going to be instruction enum dot set health. Oh shit, it's JavaScript. Yeah. We're going back and forth for maximum fun. Okay, so that's that. I'm not doing all of them. Type that in. You have written your first virtual machine. Yay. Okay, so I think actually Rust makes this so much easier than in JavaScript. That's just my guess here. So if we come to Rust, let's actually, we don't necessarily have this as like treat magic. We've learned that. These are actually just pure out functions that are sitting here. So they're not going to have any of this mute self. They're going to be reaching out and doing something else. So they're just out here for us. So what we end up having is these enum instructions. So enum instruction, which is here we're gonna have like set health, and then it's like got some. Is this just setting what the size is? I don't know. I guess like we don't even need this. Like we just have set health, set wisdom. We don't really care about storing any kind of metadata in here. And now when we have this VM, so we're gonna have a struct VM. We're not necessarily storing anything in here. So let's impl this VM, and we're gonna have a public function interpret, which is gonna take self and then guess we just take a reference self so we don't take ownership of it. All right, so we're gonna take the bytecode now. So we have bytecode, which is gonna be an array of, I guess, instructions. So it's an array of instructions. Can I do that? I can't remember if I can do that. We're gonna have size, which is an I32. And actually we don't need a size. I mean, we could do a size, but I think it's easier to just loop through these. Now we're not returning anything. Now we're gonna loop through our array of instructions. So for, should be bytecodes. So for bytecode in bytecodes. Now, is this taking ownership of it? You should probably, I mean, it is taking ownership of it. Maybe we don't want to do that. Maybe we don't. Setting values of enums is good practice if you're writing shared code compiled to low level, because some shady optimizations C compilers with sometimes optimizing their values to multiples of 2? What? That's weird. Oh, are you talking about in like C compilers? But for Rust, it's different. It's probably better. Interesting. Okay, so nowadays you don't need to do that. I'm guessing. So then we're gonna, this is where we switch. Well, there's no switch. We don't need a switch in Rust. We have match. So we're gonna match on the bytecode. And so now we know that this is gonna be a potential instruction set health. And so if it's this, what do we want to do? Well, we just want to call this set health function. So set health, give it the wizard ID of 0 and the amount of 100. And that's it. And so if we have instruction set wisdom 0, 100. And that's it. Like it's a little bit simpler, a little bit cleaner. Hi Chantilly, good morning. Some compiler implementations might switch the values if you add a new one, so setting the value ensures it's more future-proof, but whatever, not sure in Rust again. I think Rust is fine, but then again, I've never done anything like super low level like that, or that like where it makes, like I have to care about the memory that much. I think I would stay with this until I get into a problem. And then I would potentially have to then I'd learn the lesson and then we just go from there. A stack machine. To execute a complex nested expression, you start with the innermost sub-expressions. You calculate those, and the results flow outward as arguments to the expressions that contain them until eventually the whole expression has been evaluated. The interpreter pattern models this explicitly as a tree of nested objects, but we want the speed of a flat list of instructions. We still need to ensure results from sub-expressions flow to the right surrounding expressions. But since our data is flattened, we'll have to use the order of the instructions to control that. We'll do that in the same way your CPU does, with a stack. This architecture is unimaginably called a stack machine. Programming languages like Forth, PostScript, and Factor expose this model directly to the user. Okay, so we have our class VM. Okay, and so now finally we're getting into having a constructor for this. And inside of here, we're just sort of setting stack size. My guess is this is... Okay, so stack size is... Oh, I get it. That's going to be what the size is before. So that we can choose how big it is. That being said, we're going to have this stack. So this dot stack equals and its array. And we're also going to have like the max stack size of 128. Now this is also in C, so we're having to like specifically say how many we're allowed to have in this. JavaScript, we don't care. It's an array. Also, yeah, no, I'm in JavaScript. I don't know why it's upset. It's upset at me. The VM contains an internal stack of values. In our example, the only kinds of values our instructions work with are numbers, so we can use a simple array of integers. Whenever a bit of data needs to work its way from one instruction to another, it gets there through the stack. Like the name implies, values can be pushed onto or popped off the stack, so let's add a couple of methods for that. Okay, so in our VM class here, we're going to need... I knocked my mouse over. That's fun. So we're going to have push, which takes in a value. And so this is asserting that our stack size is less than this maximum stack, but we don't really care because JavaScript. So in here, we can just say this dot stack dot push the value. Now we could do something like a vector inside of Rust, so we don't have to care either. And then pop. So assert that the stack isn't empty. So we do need to do this. Now assert, I think, kills the game, or it just... what does assert do? Does it just force quit? Does it error out? Does it crash the game? Does it just exit this error? Maybe it throws. I could try like an if. So if this dot stack dot length, if that is greater than 0, then we can return. And so what's interesting here, so return this dot stack, get the stack size, and remove, like, it's not even removing it from the stack. it's leaving it on the stack, but it's now making it sound like it's not there anymore. That's actually really interesting. And setting that is fascinating. But I can actually just remove it completely myself by saying, okay, so this dot return current index, current position. So this dot length. Yeah, the book is in C++, Gentilly. So if we do length is C, assert will terminate the program, usually with a message quoting the assert statement. If its argument turns out to be false, it's commonly used during debugging to make the program fail more obviously if an unexpected condition occurs. Interesting. So I think I'm going to do this as a as an if else, and then throw an error, which would also exit out. Rest is going to be a little bit different. Okay, so if I start doing length here, so we push onto that, and this dot length plus equals to 1. So now, if this dot length is greater than 0, so we can actually just now do if this dot length is greater than 0, then we're going to return this dot stack of position length. And I guess maybe this should be size. Or like current position or something like that. We're doing size here, essentially. Then else we want to throw new error, and this is going to be stack does not have value. So we're just exiting out, crashing the program. And then there's all the other stuff like interpret too. When instruction needs to receive parameters, so then we're going to move on and can do this. There's enough here that I don't really have time to go through it right now. So what I'm going to do is I'm going to store this at the top of bytecode. Currently at. Paste that there so we can just find this again really easily. And let's go ahead, open up, get Kraken here, and save and push all this code up. So, learning bytecode. Yeah, this chapter is gonna be a doozy, it looks like. And I'm glad that I'm doing the new system where I'm not implementing it into the game immediately, because I don't think this pattern or rather, I don't think it's a good idea to implement a full bytecode like system. It's a doozy. Well, it's what's a doozy? Oh, it's huge. It's like big and crazy. Like for example, we've been going for an hour on this, and we're not even halfway through, according to my scroller here. So there is a lot to this pattern. So we are going to be continuing, but we'll be continuing tomorrow. So I pushed up the code. You can access and look at that code with the command repo. While I'm sort of doing my anything, I can bring back the stack it game. All right, and that's played through the drop command. Okay, everyone, thank you so much for stopping by and watching. We're going through this bytecode chapter, and I'm looking forward to essentially we're creating our own compiler, which I didn't think we were going to be doing as part of this book. I also didn't read through the book ahead of time, so that's why. And I'm going to be doing these tomorrow morning, every single weekday, around 7 a.m. Mountain Time. That's when I do these. Then I have to get off and go to work. So let me switch to the ending screen. I will be back tomorrow, and then we'll continue on this. We'll see how far we get, and that'll be it. Anyways, everyone, thank you for coming. Have a great day, and I shall see you tomorrow morning.